So now we're going to start looking at even degree polynomials. And a couple of them we know right off the bat, well, particularly the second degree. Second degree polynomials, remember, are quadratic, and so their graphs are parabolas. Now, here I have two rows of graphs. I'm going to fill these in as we go. Under degree 2, the quadratics, I have a sub n greater than 0 and a sub n less than 0, two different rows, right? So a sub n being your leading coefficient, all right? And so if your leading coefficient is positive with a second degree polynomial, then your parabola is opening upward. And we've seen this quite a bit already. You have this parabolic shape opening up. Of course, if your a sub n is negative, the parabola opens down, right? A negative leading coefficient opens the graph downward. And it has symmetry about the y-axis and all that stuff. Okay, so now if I jump over to fourth degree polynomials, what we'll find is that similar to the odd polynomials where as you increased in degree, the odd polynomials shot up steeper, but they were flatter in the middle. The same sort of phenomenon occurs with even degree polynomials. So with a fourth degree, you'll still have a flattening in the middle and a steepening on the ends. Okay, so basically between -1 and 1, the graph flattens out, because any number between -1 and 1, when raised to a higher power, will actually drop closer to the x-axis. It's a reverse effect because the denominator is what's really growing faster there. Okay, and so this will widen and then, or flatten I should say, and then steepen. Get that to look all right. Okay, so it's definitely going to be flatter. You can see just the way I'm sketching it. A little flatter in the middle, steeper on the ends. And of course, a fourth degree will open upward in the same way that a second degree will. Now remember, the rationale for this, we talked about with the odd functions, is when you raise, with odd functions, when you raise a positive to an odd power, it's positive, and a negative to an odd power, it's negative. Well, here, it doesn't matter which one you raise. If you take a positive or a negative and raise it to an even power, they're both going to end up being positive, right? Even powers always become positive. That's why it goes up. Now, if you multiply that by a negative, then it's going to switch everything to a negative. And same thing with the degree 4. So we're going to have this widening, or I'm sorry, this flattening in the middle and steepening on the ends. Okay, not very symmetrical, but you get the idea. Getting up into degree 6 and so forth, it's going to get even flatter in the middle and even steeper on the ends. Okay, so we're going to see something that looks like that. I don't know if I'm drawing it comparatively very well, but you get the general idea how they're morphing from one to the next. And then, of course, with a negative leading coefficient, it's going to change that to opening downward. Okay. Now, as you continue to increase the degree, those characteristics become more defined, more exaggerated, to the point where as you get really large even degrees, like x to the 20th, for instance, the graph would end up almost looking rectangular, or like part of a rectangle, right? It's going to be very steep, very flat, very steep, and you almost won't even be able to tell that there's a bend to the graph. It's going to be so, almost like corners. However, there aren't actually ever any corners on polynomials. The graphs, it's an interesting point, the graphs of a polynomial will always be smooth, continuous curves. There's never any gaps, there's never any holes, there's never any jumps in the graph at all, and there's never any corners or cusps. A corner is what we get if you have, like two lines, like an absolute value function would come to a corner, right? A V shape. those kinds of graphs have corners. Cusps are where you would have two curves or two parts of a graph that might curve into a single point like that. That would be called a cusp. So you never have a cusp, you never have a corner, you never have a hole or a gap or a jump. And polynomial functions are very nice in that way, because the only operations that are being performed generally are addition and multiplication and exponents. And those are fairly simple calculations to make, and they make for very nice graphs. Another key feature is that the domains are always all real numbers for polynomials. Doesn't matter if they're odd degree or even degree. The domains of these arrows, even though they seem to go up very steeply, which they do, they also go out left and right indefinitely. Okay, so if you were to zoom out, or if you were to view this graph from a farther vantage point, you would see these arrows never stop going left and right. Okay, so every number on the number line will correspond to a point. It's just going to be way up there or way down there, depending upon the direction of the graph. Okay, so the domains are always all real numbers. And that goes for all polynomials. Okay, even degree, odd degree, doesn't matter. All right, the ranges are what's going to change. Okay, what we saw with odd degree polynomials is that you could get it, one tail goes up indefinitely, one goes down indefinitely, and so you end up with all real number ranges. But with even degree, you're either going to get positive or negative values. You won't get all real number ranges.